Hello and welcome to another lecture. In this lecture, we're going to continue with the designing column. This time, we're going to design a column that is basically subjected to both axial force and a bending force. So let's take a look at the problem, and then we're going to explain some stuff here. It says design a square section subjected to biaxial bending of the following condition. Our PU, it's going to be 193 kips. It's already been calculated based on dead load and life load. And moment in the x direction is going to be, the bending moment is going to be 1917 inch per kip, and my in MUY in y direction, it's going to be 769 inch kip. The concrete is a 5,000 psi, and then steel is a 60,000 psi, and the size of the aggregate is 1 inch. Place the bar uniformly around the all four surface of the column. Select the column section size and reinforcing for a square column with rho g is less than or equal 4%. Last column we designed was just pure axial. This one is basically we're going to use the interaction diagram. What is the interaction diagram is, let me go to the PowerPoint here, show you for a couple of minutes. Start up from my thing. It's not this one. No, not that one. Not that one. Not that one. We're coming up to it right here. So we did this one last PowerPoint, and the last it's also on video. And then what happened if you have the load is a little bit off the center, and that when the load is off the center, it's going to cause two things: both axial compression on a column and also cause bending. And depending how far the EX, it could be right here, it could be right there, or right here, or over here. But if it's pure bending moment and there's no axial force, it's going to fail based on a bending. And if it's a pure axial force, it's going to fail on axial force, like the last example we did. But if it's between, that's a different story. This is some good reading. You want to take a look at it, and remember we learned in kindergarten that the axial compression is basically force over the area, stress is equal force over the area, and the bending stress is mc over I or my over I, and this will give us the stress for a combined stress, both for axial and bending. Kind of a little bit, we're going to use interaction diagram. That means it's mean interaction between the axial force and a bending moment. Just give you example, one of the book I used did a good job explaining this. If you look at this diagram, point A is a pure axial, so it's going to fail in axial, and point B is a pure bending, it's going to fail in bending, and then you have a between. So basically if you stay within this side over here, you're fine. If you go outside of these, like point F, outside of this lines, you're going to fail, and the failure is going to be either all axial or bending or halfway between. So let's go back to the problem. All right, so what I have done, I used Excel to solve this problem. Just take a look at these numbers. The load that is applied to this column is off center, and we are given PU, and they already have calculated the MUX and MUY, which is kind of makes it easier. So all we have to do, we got to find the size of the column, and the rebar is going to be in it. Okay, so let's get to work. Well, let me go ahead and close this down, and you should be able to see in this. That's good. First thing we're going to calculate is the phi for this is going to be 0.65. Phi is equal 0.65. So we're going to go ahead and do that nominal axial load, Pn, which is a nominal axial load. It's going to be 193 divided by 0.65, and that will give us 297. So let me just show you the Excel here. And there's the Excel. Let me clear all this stuff out. We're going to do it over again anyway. I already did this trial once. Clear all content. There we go. So our PN we just calculated was 297, And let's go back to the writing again, and then we're going to go ahead and calculate nominal m and x, and that was 1917 divided by 0.65. 1917, that was a good year, you know that. 2949, that'd be an inch kip. And then we're going to calculate mn y direction, that was 769, divide that by 0.65, and that will give us 1183 inch kip. So the next thing we're going to calculate is the resultant moment. Maybe m and r, nominal resultant moment. So basically, be a combination of those two. You know that already anyway. It's equal square root of m n x squared plus m n y squared, which is equal. We had 2949 squared that plus 1183 squared that, and that will give us 3177 inch kip. And let's go back to the Excel, put these numbers into the Excel. Okay, so we did that. MN came out 3177. We just did that, and our concrete is a 5,000 pound psi, or 5 ksi. And then we're gonna go ahead and first step we're gonna do using the Excel. So first thing we're gonna do is assume column size in inch. We're gonna go ahead and use trial and error. We're gonna use 3 different sizes. We're going to say, because this column is a square, we're going to go 14 by 14, and then we're going to go, the next one is going to be 16 by 16, and then the next column size we're going to use 18 by 18. Once we do that, then we're going to calculate the area, AG, which is the area of the column, and that's going to be right here. It's going to be equal this by power of 2, enter. So that's 196, and you grab the corner, go across, and there's the column area for all of them. And the next thing we're going to do is go to the next step. We're going to go ahead and compute KN, PN. The reason we're going to compute that, let me go back to the PowerPoint for a second. When you look at the interaction diagram, you've seen this before. You have on one side you have Kn, and on the other side you have Rn. So we're going to calculate both Rn value, and we're going to calculate the Kn value. We have all the value we can calculate these two numbers. Once we do that, then we go ahead and find the right diagram, and then we take it from there. Let's not get ahead a little bit. So going back to the Excel, and we're going to compute Kn, and the Kn equation, I think I had it right here. There's a Kn equation, which is a Pn over f prime c times Ag. So the only variable here is Ag, so I'm going to go ahead and calculate equal. Pn was 297 divided by parentheses open. Pay attention to about down here where the formula is so you can copy it. And divided by, we don't Kn, so it's f prime c times Ag, which is a 5 time. And my Ag, it's going to be right here. Click on that cell, close it, enter. And I get 0.3. So I'll grab this corner again, move it across, so I don't have to do all those again, And there it is for rest of them. The next step we're going to calculate is compute Rn. And Rn is right here by this equation. Same thing, equal. And Emma n, it was 3177. 3177 divided by parentheses open. We got f prime c, which is 5 time h. H is, ag is, I'm going to just write down ag right here. And then multiply by h, which is 14. Enter. I get 0.23. So now I'm going to go ahead and drag this across. 0.16.11. Okay, for the rest of them. We're going to go ahead and calculate gamma. And gamma is, let me go back to the PowerPoint and show you what gamma is. Ooh, we lost the picture, didn't I? Here, gamma is, this is gamma time h. And a lot of time gamma, you gotta, going back to the equation of gamma for a second. See, the equation says h minus 5 divided by h. 5 comes from here. The distance between the edge of your concrete is basically your cover, which is 2.5 inch on this side, 2.5 inch on this side. That makes it 5 inch. But if you use 3 inch cover, and that equation could be 6 instead of 5. Keep that in mind. So right here could be h minus 6 if you're using 3 inch cover, but we're using 2.5 inch cover. And we're going to calculate that. So the gamma is equal h is right here minus, I should put a parentheses around it first. Minus 5 divided by h. Enter, I get 0.64. And if I drag that across, I get those number. The next thing we're going to go ahead and we're going to want to calculate, find the correct interaction diagram. Back of any reinforced concrete book, they have all the diagram. That's one source. The other one will be ACI itself has it. ACI has it, or back of any book. If you go on the ACI website, you can download them for free. So let me go ahead and look for that. And the reason we're looking for, what we're looking for, we already have a gamma 0.64, gamma 0.69, and gamma 0.7. So we're going to use gamma 0.6, gamma 0.7, gamma 0.8. Because our numbers fall between those numbers. So let's find the 0.641. And let me go into, you can download this on ACI, has all the stuff and it's a good one. So let's, I think it's on page 50. And we're looking for the interaction diagram right here. There's a lot of them. Start out, one thing you're going to look for, make sure you have the square, rectangular square, same thing. Fy, no, it's now 4,000. So we're going to come in, that's now 4,000. Ours is a 5,000. And our steel is 60. And our gamma was 0.64. So we're going to go ahead and use this one, R5 60.6. We need this because our number is between 0.6 and 0.7. So we need the lower number and top number. And then that's one. Then we're going to use this one also, 0.7. Gamma is equal 0.7, F prime C equal 5. And we're going to use gamma equal 0.8. We're going to use all three of those. So I'm going to go back to my Excel right now. And I'm going to write down the sources right here. I copied it. So it's R560.6, R560.7, and R560.8. The next thing we're going to calculate, it's going to be, once we have the diagram, we are going to read the PG for Kn value that we have, Rn value we have for gamma 0.6 and 0.7. For this one right here, this column, we have to look at gamma 0.6 and 0.7. For this one, because we're going to look again 0.6, 0.7 because we're 0.69. Our gamma here is 0.72, so we're going to look at gamma 0.6, 0.7 and 0.8. So let's go ahead and do this one first, and you can do this other one also. Just you need to learn how we do this. And we're going to go look at the R560.6. So I did put that in a PowerPoint, so it's easier in a PowerPoint because I can draw the line. Let me see if I can find it. That's not it. I don't know where I put it. I do. Okay, there it is. This is R560.6. And our Kn value on a Excel sheet was 0.3. So I take a line from 0.3, I take right here and I put it on 0.3, though I can see it go all the way across. And then our Rn was 0.23, so I come up to the 0.23 and I put another line there, and I'm right here. Now I want to read row. This line row is 0.06. This line row is 0.07. So we are between 0.06 and 0.07. Actually, we are like halfway. 0.0. Let's call it point. This is a judgment call as much as you can, you know. So let's say it comes out to 0.064. Since this is 0.06 right here, and this is 0.07, we kind of less than halfway. So I'm going to come in back in here, and whoops, my Excel, we're going to type in right value 0.064. That was for gamma 0.6. Okay, what I can do here, let's copy this here. You can make something like that for yourself. So I'm going to bring it down here and then paste this back in here. So our gamma for 0.6 came out to be 0.064. Okay, and now we're going to go look at 0.7 and see what's going to come out to be. Okay, then we can calculate that using linear interpolation. That's now go right here. Let's fix this up. Go to your Excel, format the cell, and go to number, and let's make that to a 3 so we see everything. There it is, 0.064. So now we're going to go to gamma 0.7. All right, this is a gamma 0.7, and this one right here. See that? R560.7, our gamma is 0.7, our K and Rn is the same thing. So I plot it in and I come up with something like here, it's close to 0.048. Then I'm going to come back to the Excel, I'm going to type in right underneath it, .048. Okay, so those are the values. So for 0.7 we got here 0.048, and remember right here our gamma came out to 0.64. 0.64. So we're going to do linear interpolation. That's what I love about Excel. you can just go ahead. This is the equation for linear interpolation, or anyway, I got a video on that if you want to learn how. So now I'm going to go ahead and write, put this equation into the Excel. So my XO is going to be 0.6, which is gamma, and my YO is my rho G, which came out to be 0.064, so I'm going to put 0.64 there. And then I got 0.7 right here, which we did, and become a 0.04. Then when I tap in this, it will give me this answer. Back in here and type in linear interpolation. And that came out to be rounded out 0.058. Okay, we're going to do the same thing over here. You can go ahead and practice if you want. And they came out basically, and these are the number came out for 16-inch diameter and 18-inch diameter. And our linear interpolation came out this way. Now, once we have this, we're going to look at that this number that we just calculated for 14-inch, that's the rho, came out to 0.058. In a problem, it mentioned use 4% steel or less. So 4%, this is more than 4%. Then if we use a 16-inch, is 2%. So we're going to be between 14 and 16. So now we're going to go ahead and say, okay, for 4% or 0.04, it doesn't have 0.04, based on rho G, we're gonna say use 15-inch. I'm gonna just type in here, use 15-inch column, and that should be, we fixed that format cell. So we're gonna use 15-inch. And then we're gonna calculate the area again, AG. Just we're going to go over same thing, do all the same thing over back down here. Our AG is going to be equal this number by power 2, enter, and it become 225. And then we're going to calculate KN. To do that, what I'm going to do, I'm going to go ahead and come back on KN here. You can do the same thing. Click on this, copy, and then come down here. When you paste on the FX, the formula, and it will give it to you. They become 0.264. Then next we're going to calculate is RN. We do the same thing. I come back up here on RN. I'm going to copy it and paste the formula back in here. And become 0.11, 0.188 or 0.19. Round them off. So if I go ahead, we just go to round these up. Make it 2. There we go. And then we're going to go ahead and do the same thing. Compute gamma. And our gamma is basically equal h minus 5 divided by h. Our h is 15. So it's going to be equal, I'm just going to write down, it's easier. H is, parentheses open, H is 15 minus 5 divided by 15, enter. So they become 0.67. All right, now we're going to go ahead and find the interaction. Okay, so now we're going to find the value for gamma 0.6 and gamma 0.7, which I already have done, but let's do it together. Going back in here, our Kn value, it came out to be 0.26, which is, I got right there. That's 0.2, 0.24, 0.26 is close to it. And then this, let's adjust this. This is 0.15, 16, 17, 18, 19. So 19 is right here. Okay. So we're going to be, yeah, about right. Your number might be a little bit off, but you know, I got 0.043, you might get 0.044, but either one is fine. So I'm going to come in here in my Excel. I'm going to type in right here 0.6, 0.04. So now I'm going to go in back to plot the same thing for 0.7. So 0.7 right here, that's gamma equal 0.7. Again, our K value came out to be 0.26, 0.24, 0.26 is down here, and 19 is right there. And this line is a 0.03, 0.04, 0.034. Sounds good. So we're going to go 0.034, 0.034, and our gamma came out to become 0.67. So now I need to know what is the linear interpolation this going to come out to be. Let's just write this number down here. I forgot. 0.043, and this one came out to be 0.034, and then format. Make sure you format your number so it shows up. There we have it. And now I'm going to go plug in my formula here. For 0.6 I had 0.043. For 0.7 I had 0.034, and our number is 0.67, 0.67. So we get 0.0367. So I'm going to type in right here 0.0367. So it's going to round it up probably. Yeah, that's fine. You want to know how this came up? Let me click on this, and there it is, the equation for it. You can write the equation down, and it's based on here. You can pause the screen and do it. So now we have got to this point. The next point behind that, we're going to go ahead calculate the area of the steel, right? And area of steel, AST, is equal, we know that, rho G time AG. And that's equal our rho G is right here, multiplied by our AG came out to this number, enter. So our area of steel comes out to be 8.2. Now you, the designer, normally when you do that, use one higher. So let's say use 9.5, round it out, 9.5 inch square. So for an area of 9.5 inch square, let me look at the PowerPoint. 9.5 inch square, we can use 9.5 be 9s. What about that? If we use 8, that'd be 1 inch for corner, 1 in the middle, that makes it 8, right? So that'd be 8 times 127, and whatever that comes out to, 8 times 127. Let's go ahead and come back in here. Okay, so if we come back down here, our H came out to be 15 inch. So B also comes out 15 inch. And then we're going to use rebar. The rebar AS came out to be AST. Area steel came out to be 9.5 inch square. So if I put one right here in this corner, one in the middle right here, one in here, one in there, one in here, one in here, one in here, one in here, 1 2 3 4 5 6 7 8. So 8 will be if I use 8 times number 10, say 8 number 10, and that become 8 times 1.27. I don't know what that number comes out to. Give me a second. You can use that. It might be too heavy. Then you go 1016. So 10.16 divided by the gross cross-sectional area was 225, and that become 0.045. So that's not bad. That's pretty good. All right. I hope you liked it. Subscribe, give it a thumbs up, whatever you gotta do. Have a wonderful day.